In this video, we will discuss how to estimate the size of nanoparticles from their UV-Vis absorbance data in Origin. First, we will talk a little about the metal nanoparticles. Nanoparticles are ultrafine particles in the size of nanometer, which are generally in the range 1 to 100 nanometer, however less than the submicron particles. The definition of nanoparticles differs depending on the materials, field, and applications concerned. All the solid particles consist of the atoms or molecules. As they are micronized, they tend to be affected by the behavior of atoms or the molecules themselves, and to show different properties from those of the bulk solid of the same material. It is attributable to the change of the bonding state of the atoms or the molecules constructing the particles. The diameter of the smallest hydrogen atom is 0.074 nanometer, and that of the relatively large lead atom, having atomic number 82, is 0.35 nanometer. From these sizes, it is estimated that the particle with a size of 2 nanometer consists of only several tens to thousands of atoms. Micronization of solid particles lead to an increase in the surface area compared to the particle size, which causes dramatic changes in structural and optical properties. The unique features of nanoparticles depend critically on their size, shape, and morphology. The two key parameters of nanostructures are the size and shape, which have a crucial role in their properties and diverse applications. These key parameters are usually determined using electron microscopic techniques such as SEM and TEM. Although these techniques are very powerful in determination of size and shape, but the problem is that these techniques are too expensive and not at hand anywhere and anytime compared to optical spectroscopy. The optical properties of metallic nanostructures are determined by the collective resonant oscillations of their conduction electrons with respect to the positive ion background known as plasmon, which relates the extension coefficient to the size and geometrical properties of metallic nanostructures. Therefore, optical spectroscopy is one of the simplest and easiest ways to determine the geometrical properties of metal nanostructures, including their size and shape. One of the unique features of metal nanoparticles is the surface plasmon resonance, which is exploited in optical spectroscopy to estimate the size and distribution of these nanoparticles. For example, in this article, radius of a nanoparticle is calculated from the Fermi velocity, surface plasmon resonance, and full width at half maximum. In this article, the average diameter is calculated from the location of the surface plasmon resonance. However, I prefer to calculate it with the Hayes equation. I prefer it due to its accuracy because in this equation the two parameters L1 and L2 are adopted from the fitting of the size from transmission electron microscopy versus the one calculated from the absorbance data. L1 and L2 parameters comes out to be 6.53 and 0.0216 respectively. However, it is to be noted that these calculations are for the colloidal metal nanoparticles, which are spherical in morphology and uniformly distributed in a solution. Further, this equation is true for the particles' diameter ranging from 25 to 110 nanometer, while for the nanoparticles less than 25 nanometer, other equations are utilized. In this equation, D is equal to the log of lambda SPR minus lambda naught over L1, which is whole divided by L2, where lambda SPR is the wavelength at which maximum absorption occurs, Lambda naught is the wavelength at which minimum absorption occurs at the start of SPR. While as mentioned earlier, L1 and L2 are the values taken from the data fit of TEM versus UV-Vis, whose values are L1 equal to 6.53 and L2 equal to 0.0216. Now we will go to the data file in Origin to get the values of lambda SPR and lambda naught from the plot. This is the wavelength versus absorbance data of gold nanoparticles. Let us plot the data and do some rescaling to the graph for a good look. Now to find the lambda SPR and lambda naught, we will use the zoom and the data reader tools to find the values accurately. First, we will find the lambda naught value, which is 473.57. And lambda SPR value is 529.37. Now put these values in the Hayes equation. The value of lambda SPR minus the value of lambda naught divided by L1, take the natural log and then divide the whole result by L2. The value comes out to be 99 nanometer. This value is perfectly accurate as these nanoparticles were already measured with TM as 100 nanometer. In the forthcoming video, I will calculate the size of nanoparticles with the help of Mie theory, whose equations are simulated in a Mathematica code, which not only give the size but also the morphology and distribution of the metal nanoparticles. Thanks for watching the video.